I'm really excited to finally sit down and talk a bit about how video works, because most people, even engineers, don't seem to understand it very well. So if you're a coder or not, I think this will be an interesting deep dive in how H.264, the codec that powers most of the video on the internet, actually works. Thankfully, I don't have to do too much research here, because Sid Bala wrote an awesome article all about this that is just as relevant now as it was when written back in 2016. There are new codecs, and we'll talk a bit about those near the end, but the focus here is H.264, which is almost certainly the technology that you're using to watch this video right now. H.264 is magic. H.264 is a video compression codec standard. It is ubiquitous. Internet video, Blu-ray, phones, security cameras, drones, everything. Everything uses H.264 now. Some things use H.265 now, but 8 years ago, we'll give them some credit. H.264 is a remarkable piece of technology. It's the result of 30 plus years of work with one single goal: to reduce the bandwidth required for transmission of full motion video. Technically, it's very interesting. This post will give insights into some of the details at a high level. I hope to not bore you too much with the intricacies. Also note that many of the concepts explained here apply to video compression in general and not just H.264. I'll be sure to point out which that is the case for. Why even compress anything? Well, a simple uncompressed video file will contain an array of 2D buffers containing pixel data for each frame. So it's effectively 3D. It's the 2D for the picture, and then one additional dimension that is time. So you have each frame that has a pixel and data for every single pixel in that picture, and you have a new one for every picture over time. And as stated here, each pixel takes 3 bytes to store, 1 byte each for the 3 primary colors: red, green, and blue. You might be confused a bit, because if you remember primary colors, you might remember that they're not red, green, and blue. They're actually red, blue, and yellow. And with those 3, you can theoretically make every color. Why does this matter though? Well, every pixel on your screen isn't just a dot that lights up a specific color. It's usually a combination of 3 dots that change their brightness in order to combine into a color. If you look at a pixel really close, you'll see that it's usually 3 stripes or some similar pattern, where you have a bright red, a bright green, and a bright blue. By mixing how much of each of those colors is visible, you end up seeing a different color when you look at it from further away. The reason that green was chosen instead of yellow is pretty specific. It's the concept of additive color palettes, where you increase the amount of different colors in order to change the colors and access more things. So if you add more color, if you add all red, all green, and all blue, you get white. This is important because this brightness level is something that's important with your monitor, because you want to be able to make things brighter, not darker, when you want to increase colors. And theoretically, if you got to white by removing a bunch of things, that wouldn't work. The other way you can generate all colors is through the CMYK color format, where adding more colors makes things darker, because it's, as they state here, it's effectively like pigments on printed materials, so they're layering on top of each other. There are 2 different methods for combining light, and RGB is the one that made the most sense for monitors, because when you combine the colors, things can get brighter. So now that we know all of this, we should go back to thinking about how the actual H.264 algorithm works, because each of those pixels needs to be representing a certain level of red, of green, and of blue. That's how a hex code works. It has those 3 parts where you have the red amount, the green amount, and the blue amount. So now you need all 3 of those numbers for every single pixel in your screen. That's 3 hex digits, so 3 hexadecimal numbers, times the number of pixels width, times the number of pixels height. You end up with insane amounts of data. And as he says here, 1920 by 1080 times 60 times the 3 bytes to store the pixel for each of those 3 colors. You end up with 370 megabytes per second. That's a megabit. That's megabyte. That's double a gigabit internet connection. That's insane. That's absurd bandwidth that a single 10-second file would be 2 to 3 gigs. That's insane. And we can't do this. It's obvious that this is not how the internet works. And when you watch this video at 1080p 30 or even 4K, you're not downloading a terabyte of data. So how do we deal with this? We need to compress. As he says here, a 50 gig Blu-ray would only hold 2 minutes of uncompressed 1080p 60. That's crazy. 50 gigs is 2 minutes. Absurd. Even my streams, which are hours long, a 5-hour stream uncompressed with my recording methods with H.264 are like 400 gigs for 6 hours. 50 gigs for 2 minutes is unfathomable. So we have to compress this. So why H.264? This is an interesting intro. Yes, I'll answer, but first let me show you something. Here's the Apple homepage. I captured this screen because the homepage produced 2 files. It's a PNG screenshot of the Apple homepage and 5 seconds of 60 FPS H.264 video of the same Apple homepage, 175K. Why is the PNG a megabyte and the 5 seconds of video are 175K? What? Those file sizes look switched. No, they're right. H.264 video, 300 frames long, is only 175K. A single frame of that video in PNG is 1015K. I actually made a video about the smallest possible PNG, so if you're curious about how PNG compression works, check that out if you haven't. Looks like we're storing 300 times the amount of data in the video, but the file size is a fifth. So H.264 would seem to be 1,500 times as efficient as PNG. How is that even possible? All right, what's the trick? Well, there's a lot of them. H.264 uses all the tricks you could think of, and tons you probably didn't. Let's go through the important ones. So, Part 1, shedding weight. Imagine you're building a car for street racing. You need to go faster. What is the first thing you do? You shed some weight. Your car weighs 3,000 pounds. You throw away stuff you don't need. Back seats, chuck them. Subwoofer, gone. No music needed. Air conditioning, yeah, ditch it. Transmission, yeah, wait, you need the transmission. You remove everything except the things that matter. This concept of throwing away bits you don't need to save space is called lossy compression. And obviously, H.264 is a lossy codec. It throws away less important bits and only keeps the important ones. This idea of lossy versus lossless is really important because there are compression methods that take some data, find common patterns in it, and then make a table of those patterns. So you can take that data and represent it with something smaller by taking the reused pieces and giving them like assigned values. So it's basically a lookup table for all the parts of your thing so that it's still lossless, because you have all that data there, but you have to do a lot of decoding steps in order to get that data out. H.264 does not work that way. They're optimizing for and actively seeking things they can delete that will no longer be there once you decode and play back that video. It is choosing to remove data in order to make it more efficient, versus something like a PNG, which behaves more like what I was describing there, which would be something like a RAR or a zip, where it is making those exact lookup tables so that it can recreate the exact file. And PNGs are lossless. They don't throw away anything. Bit for bit, the original source image can be recovered from a PNG encoded file. But what's an important bit? How does the algorithm know what bits in my frame are important? There's a few obvious ways to trim in images. Maybe the top right quadrant is useless all the time. So maybe we can zero out those pixels and discard the quadrant. We would only use 3/4 of the space we need. Now we're down to 2,200 pounds. Or maybe we can crop out a thick border around the edges of the frame, but the important stuff's in the middle anyways. Yes, you could do all those types of things, just crop stuff out, but that's not what H.264 does, because it needs to represent everything or people would think it's broken. So what does H.264 actually do? H.264, like other lossy image algorithms, discards detail information. Here is a close-up of the original compared with the image post-discard. We'll zoom up really close, and I'll be honest, this will be a bit harder to see in the official video that you'll be watching on YouTube because YouTube is doing its own compression. But to me, sitting here is incredibly clear, and I'm sure you'll still see it due to the amount of compression happening. The edges are way cleaner here. And here, especially where the colors are changing, there's almost like a wobbly like warping. And you'll also see a little bit of like pixelation with that color, even though it's a flush color with a little bit of shadow here. You can pretty obviously see the detail loss here, and I hope that comes through in the video you're watching in the end. But let's keep going because we need to understand how this works and why it happens. See how the compressed one does not show the holes in the speaker grill in the MacBook Pro? I didn't even look at that. So we have all the holes here. And here they're all blurred into like a gray bar. If you don't zoom in, you might not even notice. Like we can see here, these are indistinguishable. Once you zoom in, it gets really clear. The image on the right weighs in at 7% the size of the original. We haven't even compressed the image in the traditional sense. Imagine your car just weighed 200 pounds. 7%? Wow. How did you discard detail information like that? Tricked you guys, we're talking about math now. Information entropy. Now we're getting to the juicy bits. Ha, puns. That was a good one. If you took an information theory class, you might remember information entropy. Information entropy is the number of bits required to represent some information. Note that it is not simply the size of the dataset, it's the minimum number of bits that must be used to represent all the information contained in that dataset. Similar to what I was talking about earlier with the encodings. For example, if your dataset is the result of a single coin toss, you need 1 bit of entropy. If you have to record 2 coin tosses, you need 2 bits. Make sense? Suppose you have some strange coin. You tossed it 10 times and every time it landed on heads. How would you describe this information to someone? You wouldn't say H. You would just say 10 tosses, all heads. Bam. You've just compressed some data. Easy. I've saved you hours of mind lectures. I love this article. This is so well written. This is obviously an oversimplification, but you've transformed some data into another, shorter representation of the same information. You've reduced data redundancy. The information entropy in this data set has not changed. You've just converted between representations. This type of encoder is called an entropy encoder. It's a general purpose, lossless encoder that works for any type of data. So that's the first piece. Next is the frequency domain, which combines that in an important way. Now that you understand information entropy, let's move on to transformations of data. You can represent data in some fundamental units. If you use binary, you have 0 and 1. If you use hex, you have 16 characters. You can easily transform between the two systems. They are essentially equivalent. So far, so good? Let's go. Now, some imagination. Imagine you can transform any data set that varies over space or time. Important detail at the time. We'll get to that soon. Hopefully, some of y'all are starting to figure out how time comes into play. Something like the brightness value of an image into a different coordinate space. So instead of XY coordinates, let's say we have frequency coordinates. Frequency X and frequency Y are the axes now. This is called the frequency domain representation. It's another binary mathematical theorem. I love that he's very real about these being crazy math things. And this theorem states that you can do this for any data and you can achieve a perfect lossless transformation as long as the frequency of X and Y are high enough. Okay, but what the freak are freak X and freak Y? Great question. Freak X and freak Y are some other sets of basis units. Just like when we switch from binary to hex, we have a different fundamental unit. We're switching from the familiar XY to frequency X and frequency Y. Hex A looks different from binary 1010. Both mean the same thing, but look different. So here's what our image looks like in the frequency domain. This is where things get interesting, because obviously this is not that image, but this represents it. The fine grill on the MacBook Pro has high information content in the higher frequency components of that image. Finely varying content equals high frequency components. This is a piece that's going to come up a lot. Things that vary a lot. The classic example of this is confetti falling, where every few pixels is changing every frame or two. We'll show some examples of that in a bit. Finely varying content equals high frequency components. Any sort of gradual variation in the colors and brightness, big example of this is gradients, are low frequency components of that image. Anything in between falls in between. So fine details equals high frequency, gentle gradients equals low frequency. Make sense? Here's the classic gradient example that should hopefully come up well, depending on what resolution and quality you're watching the video at. On the left, we have an 8-bit gradient where we have 8 colors that represent all of the things here. With the 8-bit gradient dithered, we've done more to blend, usually by blurring and mixing those 8 bits. And then we have the 24-bit gradient where we have 24 colors to represent it. And you'll see how much smoother this gradient looks than either of these, but more importantly, how awful this one looks. Have you ever seen this weird ringing pattern in a video? It's because it was aggressively compressed, and going from one color to another when you have a limited set of colors is really, really hard to do. So as he said, the dots for the speaker grill here are an example of high frequency. The pixels left and right are constantly changing for each of these dots, which makes it hard to compress. In the frequency domain representation, the low frequency components are near the center. The high frequency components are towards the edge. Okay, kind of makes sense. Why do all this? Because now you can take the frequency domain info and then mask out the edges. Discard information which will contain the information with high frequency components. Now, if you convert it back to your regular XY coordinates, you'll find that the resulting image looks similar to the original, but has lost some of the fine details. But now the image only occupies a fraction of the space. By controlling how big your mask is, you can now tune precisely by how detailed you want your output images to be. Here's a close-up of the laptop in the homepage again, except now there's a circular border mask that has been applied. This model represents how frequent changes occur. So how much difference is there between 2 pixels next to each other? Towards the middle, there is very little change. And towards the edges, there's a bunch of change. So things that change constantly, like that speaker grill, where every other pixel is very different, those types of things would be out on the outside here, where the things that are pretty consistent, like the black around the delete button, that'd be near the middle, because it doesn't change a whole lot in that space. So if you plot things like this, such that the things that change the most are on the outside and the things that change the least are on the inside, and then you compress towards the middle, so you only keep the parts in the middle, you throw out everything else, you end up with significantly more efficient data storing, which you can see here. This tiny little circle of the most changing parts in the middle. If you take this 2% trim, where you have just the most common recurring patterns and pieces, the things that are the most consistent, and you throw out everything else, you effectively smoothed all the parts that change the most, which is why when you zoom in, you see the speaker grill getting all blurry, and you see the skin tones on the hand getting all chunky. Because even here at 11%, that little jump in how much space you had, all of the texture for your skin there must have existed in that range, in that level of change. Whereas the speaker grill clearly existed a little further out, which is why you could still see it a bit at the 30%. It starts to get messy at 11, and then it's entirely unreadable at 2. It's a really good visualization of how this entropy works and how you can visualize it. The numbers represent the information entropy of the image as a fraction of the original. As I say, even at 2%, you won't notice the difference zoomed out. Look here, those all look exactly the same. And to go back to the car example of the 3,000-pound car, we're now down to 60 pounds. So that's how you shed weight. This process in lossy compression is called quantization. Really important part of how this all works. Okay, impressive, I guess. What else you got? Here's one of my favorite bits. Chroma subsampling. The human/I brain system is not very good at resolving finer details in color. It can detect minor variations in brightness easily, but not color. So there must be some way to discard color information to shed even more weight. In a TV signal, RGB color data gets transformed into Y plus CB plus CR. The Y is the luminance, essentially the black and white brightness, and the CB and CR are the chrominance components. Chrominance is color, if it wasn't clear. RGB and YCBCR are equivalent in terms of information entropy. Why complicate things, though? Is RGB not good enough? Well, back before we had color TV, we only had the Y signal, because we only had white and black, and then the brightness level of the white. And when color TVs just started coming along, engineers had to find a way to transmit RGB colors along with the Y. Instead of using two separate data streams, they wisely chose to encode the color information into CB and CR and transmit that along with the Y information. You might be able to guess the cool thing here, stated clearly. This way, black and white TVs would only have to look at that Y part, and they would still work. If you just take the brightness levels, that's black and white TV. But if you have a color TV, they'll also look at those other components and use those to make a color image converted to RGB. But check out the trick. The Y component gets encoded at full resolution. The C components only at a quarter resolution. Since the eye and brain are terrible at detecting color variations, you can mostly get away with this. By doing it, you've reduced the total bandwidth by half with very little visual difference. Half. Your car now weighs 30 pounds. Yes, we just threw out a ton of that color data, and since the human eye is fundamentally flawed, it doesn't really matter. This process is called Chroma subsampling. While not specific to H.264, it's been around for decades, it's pretty universal. Everything does some form of Chroma subsampling. Those are the big weight shedders for lossy compression. Our frames are now tiny, since we discarded most of the detail information and half of the color too. Wait, that's it. Can we do something more? Yes. Weight shedding is only the first step. So far, we've only looked at spatial domains within a single frame. Now it's time to explore the temporal compression. We look at groups of frames. I'm going to quickly diagram this before we go in too far, because I want to make sure this part is really well understood because it's super important. Here's a frame. This frame has text that says, "Hi." All the stuff we just talked about can explain how we would or wouldn't compress this. But we're not talking about one frame. We're talking about a bunch of them. Let's say in the next frame, I add an exclamation point. Most of this frame didn't change. Most of the data for the hi is still there, and everything that isn't this exclamation point is the same. So we need a way to encode that. Another way of thinking of this, and this is what I really want to push, I like the dimensional argument. Now I want you to pretend that this is 3D. So now we have this 3D object where the front is this hi frame. Now I want you to imagine that next frame that would come after. We can't quite see it because it's blocked here. That's what this frame is. So think of this high exclamation point frame as behind this original high frame. And this is what the author means when he says that video is three-dimensional, because you're taking all of these 2D images, and as time passes, they're changing. So every layer is going backwards an additional dimension, but we know the thing that was before it. We can probably use that for something, right? Let's go in and figure out what we can do here to make yet another very important optimization. You might be curious about how these color conversions work. I understand why. They're really interesting. This would be its own whole, probably very long video. So I'm just going to link this Wikipedia in the description, so you can go read about it if you want to yourself. I'm going to do that because I don't want to get sidetracked even more than I already have been. This is a video about video compression, not color encoding. Still really cool stuff. Go check it out if you're curious. Weight shedding is only the first step. So far, we've only looked at the spatial domains within a single frame. Now it's time to explore temporal compression, where we look at a group of frames across time. Motion compensation is the first part here. H.264 is a motion compensation compression standard. That's a set of words. What the hell is motion compression? Well, imagine you're watching a tennis match. The camera's fixed at a certain angle. The only thing moving is the ball back and forth. Obviously, other things will be moving, but it's theoretical. Imagine just that ball is moving. How would you encode this information? You do what you always do, right? You have a 3D array of pixels, 2 dimensions in space, and 1 in time, right? So every time you get a new frame, you need all that data. That's chaos. Why would you do that? Most of the image is the same anyways. The court, the net, the crowds, all these things are static. The only real action is the ball moving. What if you could just have one static image of everything in the background and then one moving image of just the ball? Wouldn't that save a lot of space? You see where I'm going? Get it? Motion estimation? Let's dive in. Lame jokes aside, this is exactly what H.264 does. H.264 splits the image up into macro blocks, typically 16 by 16 pixels, and they use these to do motion estimation. It encodes one static image, typically called an iframe, intraframe. These are important because they're a full frame containing all the bits that are required to construct that frame. An iframe is pretty much your traditional image. It's just the pixels that render that image. But then the subsequent frames are where things get interesting. They're either called P-frames, which are predicted, or they're B-frames, which are bidirectionally predicted, where it uses data on both sides. P-frames are the frames that will encode a motion vector for each of the macro blocks for the previous frame. frame. That's a bit of a word soup if you're not already familiar with video encoding. Better way to put this is, if we go back to my diagram here, this first frame would be an iframe, that is all that data. And the next frame would say, hey, these pixels changed to this information. So as unintuitive as it might seem, that frame won't have any of this data in it because that all comes from before. Just the thing that was added is encoded in that because this is the change. B frames and P frames are kind of change frames. To go to the Git example, this is the init commit, and then each of these are diffs that are changing what that frame looks like based on specific pixels changing. We'll go way more in depth on this as we read along. So P frames are frames that will encode a motion vector for each of those macro blocks. So each of those 16 by 16 chunks, a P frame describes if it changes and how it changes. So a P frame has to be constructed by the decoder based on the previous frame. It starts with the last iframe in the video stream and then walks through every subsequent frame, adding up to the motion vector deltas as it goes along until it arrives at the current frame. This is very important because it's not free. If I have this frame and I want the next one, I apply this diff and I have the next one. Cool. What if I'm at this frame and I want one 7 frames down? What if I start 7 frames down and it's a P frame and I actually want to see what it is? Now I have to go all the way back until I find the first iframe and then apply these changes for every frame until I'm at where I want to be. This is also why video editing software is so complex and difficult, because when you skim through a video and chop at a point, usually it has to generate a new iframe at that chop point in order for any of this technology to work. If you've ever seen video where like a scene changes, where it cuts to some other video and everything gets super artifacty and like little black chunks floating around and stuff, that's because it's referencing the wrong iframe. And then you get a new iframe and suddenly everything goes back to normal. That's just P frames though. It can actually get crazier once you talk about B frames, because the prediction goes both ways, from the past frame and from future frames. So now you can imagine why the Apple homepage video is so well compressed. It's really just 3 iframes, which again are the key images that represent the site, and those are already super compressed. And now you just have motion data between those frames. So despite the video being 5 seconds long and 60 FPS, you're actually only getting 3 images with it, all of which are compressed, and then a bunch of change data between those different frames. Let's say you've been playing a video on YouTube. Hopefully you're already subscribed to what? Well, I guess the author's a fan. If you haven't already subscribed, you know that it's free, right? It's a little button at the bottom of the video. You just click it. Helps the channel out a ton. And you can see more things like this. The blog post author didn't put that there, by the way. I just inspect elemented, but I'm doing my job, okay? Hit the subscribe button. This video has taken so long to film. Anyways, you missed the last few seconds of dialogue, so you scrub back a few seconds. Have you noticed that it doesn't instantly start playing from that timecode you selected? It pauses for a few moments and then plays. It's already buffered those frames though, since you just played it. So why the pause? Yeah, that annoys the shit out of me. Why does it do that? Well, I was actually hinting at this earlier with my own video editing experience. Your computer has to decode a bunch of stuff. You just ask the decoder to jump to some arbitrary frame. So now it has to redo all the calculations, starting from the nearest iframe and adding up the motion vectors till it gets to the frame that you're on. And that's computationally expensive, and hence the brief pause. Hopefully you'll be less annoyed now, knowing that it's doing actually hard work and not just sitting around. Have you ever heard of hardware encoding and decoding? Usually this is what it's referring to. The ability for a graphics processor, or even like a traditional CPU, to take one of these crazy video feeds and quickly, efficiently get to that iframe and generate the frame you're supposed to be on. In order to do that, you don't need one really powerful processor. You need a ton of tiny ones to manage each of those 16-bit chunks. This is one of those tasks that graphics cards are really good at, because they don't have 1 to 16 big, really powerful cores like a normal processor does. They have hundreds, if not thousands of small ones that do really quick changes. And efficient hardware encoders and also decoders work really well because they're checking each of those 16 by 16 chunks for every frame. And when you have a bunch of those chips doing that little bit of work for every frame, it's way faster than if you have a small number of chips doing that work instead, even if they're way more powerful. Hope that helps demystify why hardware acceleration and hardware encoding and decoding are as important as they are. Since you're only encoding motion vector deltas, this technique is extremely space efficient for any video with motion at the cost of some computation. This is a very important point to understand. You're trading space efficiency for compute efficiency. You could send videos that are just iframes, so you don't need to generate that data. In fact, the camera I'm recording on right now has an all iframe option. The videos are way bigger. They're so much bigger you can't even record them on an SD card. You have to record them on an external hard drive for it to work. And it has to be a fast one, like an external, like fancy SSD. But when I use that in my video editor, it works way better because it doesn't have to generate the frames between the iframes. It just has them. So when I say go to this point, it just goes there. But in order to do that, I have to take up way more space. If I don't take up that space, then I end up having way more data usage instead. If I choose to save that space by doing B frames and having this motion compression, I end up having to decode that when I play it. So Effectively, you could argue YouTube is making everyone's devices do more work and wasting all of our batteries in order to save storage costs. It's much more intricate than that because bandwidth is expensive for everyone involved. But effectively, YouTube and platforms like it have made the decision that they will store smaller files, send you a smaller file, and now your processor has to do the work to play it. And that's a very, very good trade-off. Cool. Now we've covered both the spatial and temporal compression. So far, we have a shit ton of space saved in quantization. Chroma subsampling further halved the space required. On top of that, we have motion compensation that stores only 3 actual frames for the 300 that were in that video. Looks pretty good. Now what? Well, now I wrap up and seal the deal. We use a traditional lossless entropy encoder because why not? Let's just slap it in there for good measure. That was what I was talking about earlier with like the zip type compression where you have these things that are recurring, so you put them in a table to look them up. Really good stuff. Entropy coder. The iframes, after the lossy steps, contain redundant information. The motion vectors for each of the macro blocks in the P and B frames, there are entire groups of them with the same values, since several macro blocks move by the same amount when the image pans. This is actually a really good example. If we go back to this wonderful high frame, let's say that for the next 3 frames, the camera pans. So next frame, it's here. Next frame, it's here. Next frame, it's here. And it keeps doing that over time. The way this is described in the B frames would be these pixels shifted this amount. And if you do that over and over, maybe detailing, hey, pixel X42, Y43 moved right to, and doing that over and over again might not be the most efficient way to encode that data. As such, if we can represent that move, if we can represent this pixel moved this amount with some random thing instead that isn't as much data, and we just said that over and over instead, that'd be way more efficient. Think back to the 10 H's from the beginning of the video. It's like that, but instead of it being for pixels, it's for movement. And if movement is consistent, you can represent it with traditional lossless compression way better. But if the movement's inconsistent, like my favorite example, confetti, that doesn't work at all. So as I was hinting at there, an entropy encoder will take care of that redundancy. If there's redundancy between those motion frames, it can smooth that out for you. And since it's a general purpose lossless encoder, we don't have to worry about what trade-offs it's making. We get all the data we put in. And now we're done. At the core of it, this is how video compression codecs like H.264 work. These are its tricks. Okay, great. But I'm curious to know how much the car weighs now. So the original video was a weird resolution, 12321154. If we apply the math, it would be 1.2 gigs if we just took the raw frame data. But now when we've compressed it through H.264, we get 175 kilobytes. So to go back to the 3,000 pound car, we got it all the way down to 0.4 pounds. Wow. When you put it in this context, like comparing the car weights, this is an actual miracle that this technology exists. Without it, none of the things we're doing now would work. Y'all certainly wouldn't be watching me on YouTube, and I probably wouldn't even have this career. Most of my adult life has been spent working on video in some form, from working on it at Twitch, to building collaborative music experiences, to building tools for creators to do live collaborations. All of this is possible because of H.264 and codecs like it. Yeah, as the author says here, this is a massive oversimplification of several decades of intense research in the field. If you want to know more, the Wikipedia page is pretty descriptive. You'll be amazed at just how detailed these Wikipedia pages are about a lot of these things, because the same nerds who sit there mathing their way through it are the nerds who keep Wikipedia up to date. And since a lot of these codecs are older and very well battle tested, these articles tend to be very, very accurate, which is a great source of information. Have comments? Did I get something wrong? Not a fan? Use Hacker News? Nah. What I'm going to do is I'm going to follow you on Twitter because this article was incredible. And sadly, it looks like you haven't used Twitter since 2018. Your article posted in 2016. But Sid Bala, you made something awesome here. This is one of the best breakdowns I have seen of how video compression works. There's a great video by Tom Scott about specifically how snow and confetti ruin YouTube video quality, which is secretly a video all about video encoding. I highly recommend watching it, and I'll drop it in the sources if you haven't seen it already. But I want to showcase the confetti bit so you can see just how bad it gets quick. You won't be able to hear the audio because my setup is screwy, but you can go watch the original if you're curious. So here we see it at a low bitrate. You can see how all the motion causes really bad and jank blurring. You can even see when the keyframes and the iframes happen, because you'll see it goes from super blurry to really sharp all of a sudden. Did you see how quick that motion jumped? It's all about this. But this low bit rate, especially once you get more and more motion happening and there's not enough room in the data you have, you end up with way choppier motion and things just slowly falling apart. And that's because there isn't enough data being encoded here because they have a hard limit on how much data they're putting in the video. Getting all that motion and that little data just falls apart. Your computer's not lagging. Like, look, I'm nice and smooth, but since that data rate was so bad, it fell apart. But then when you bump up the bit rate to a much higher value, suddenly the motion gets way smoother. Now that this motion's gone through my stream, my video editing, my upload, and then to you, it might not look as good. So again, check out the Tom Scott video. It's incredible. But hopefully this helps showcase just how important these technologies are and how they do and don't work. Oh God, I love that moment too. You have to go watch the original video. But when he freezes the motion, everything is suddenly super sharp because it's no longer struggling to just fit all the motion in the data you have. And since things are staying, you can rely on iframes more, and that motion data that you have in the B frames can be focused on the little bit that does move. This is such a good example, and I highly recommend checking it out if you're curious. That's all I have to say. The author did an incredible job. Huge shout out to Sid Bala for writing this. Great blog post. Appreciate y'all a ton. If you want me to talk more about video, audio, images, and how these things work, I'm a big AV nerd and I'm always happy to do it. That's all I have to say for now. See you guys in the next one. Peace, nerds.